Okay, we're back for the rest of chapter 15 on fluids. And we're going to talk about Archimedes' principle. And Archimedes said that any material that is more dense than what it is in will sink. If its density is the same as what it's in, it will float. Or if it's less than that. Okay, so this is telling us, this is relating the density of the substance that's floating compared to the volume. So it's saying that for the submerged amount, that's going to be equal to the volume of your solid. That's going to be the density of your substance or your solid, and then this would be the density of the fluid. And so this is going to tell you the volume of this part that is submerged in the water. All right, we're going to look at continuity, and continuity says that the volume of fluid per second in a tube or any kind of a pipe is the same at every point. So that means if the pipe is narrower, then the flow has to be faster. It has to be faster in order to have the same volume of fluid go through there each second. And this relates us to the continuity equation. So if I have a tube and it has two different areas, so I can see here that this has a much larger area than this section over here, then that means the part where it's narrower, the velocity has to be more than this one. Because this one, if I want to have the same amount of fluid go through this each second in the narrower region, it's going to have to go faster. So the equation that we use is ρ1, and remember rho is density, times the area 1 times the velocity 1 is ρ2, area 2, velocity 2. And as long as you're talking about the same fluid, like if you have, in this case, a water pipe, that means the densities are going to be the same. So then you could get rid of those densities if it's the same fluid. Okay, for most gases, they're easily compressible, but liquids are not. And therefore, the density of the liquid is constant. So that's where I deleted those rows, those densities, and you can see this is our continuity equation if you have a fluid. Okay, so that means whenever I go from a wider area into a smaller area, we know that the speed is going to increase because work was done on it. So here we have an example. We have a river and it narrows at a rapids. It goes from a width of 12 meters to a width of 5.8 meters. The depth of the river before the rapids is 2.7 meters, and the depth in the rapids is 0.85. They want me to find the speed of the water flowing in the rapids if the speed before the rapids was 1.2. And they tell me to assume that the river has a rectangular cross-section. That means when we find the area for a rectangle, we do length times width. In this case, it's width and depth. So to find my area, I took 12 times 2.7 because this was the width that I had before and the depth that I had before, times the velocity that I had before. And on the other side, this is going to be the width and the depth afterwards, so the 5.8 and the 0.85. And then I found V to be 7.9 meters per second. So that's how you would use the continuity equation. Now we're going to look at Bernoulli's. And Bernoulli's equation is pretty much a different way of writing the conservation of mass. Excuse me, not the conservation of mass, conservation of energy. So here we have 1/2 rho v squared. This is like your kinetic energy. It's 1/2 mv squared. So this is kind of like your kinetic energy term. And then we have this, which is our potential energy term, where we had mgh. So the only added term is this pressure. So basically I have kinetic energy, potential energy, and now pressure energy. And so this is going to be the equation that we're going to use for our conservation energy of fluids. Now this equation is really nice because we can eliminate terms if I don't need them, which means if the height doesn't change, then I can just eliminate this whole term. Or if the speed doesn't change in my fluid, then I just leave out this term. So we'll go through an example so you can see how that works. Okay, so in this case I have a garden hose and it changes diameter and they want me to find the speed. So this was back to that continuity equation. So in this case, since this is a pipe, then to find my area I have to do pi r squared. So I did pi r squared times v, pi r squared times v. These should be in meters, but since I left them in centimeters on both sides, it won't matter. So you don't have to change them in meters as long as you leave them both in centimeters or whatever your unit is. So I went through and the pi's could cancel out. You wouldn't need to have those. And I went and found the velocity was 8.1. Now there's a second part of this question, and the second part deals with Bernoulli's. So it gives me all that same stuff, and then it says when it gets to the nozzle, they want me to find the pressure of water in the nozzle. So now I'm going to go through this Bernoulli's equation. All right, so there is no change in height. So that means this term can go away. All it does is change the diameter of the pipe. And I cannot have it in atmospheres, the pressure that they gave me in atmospheres. I can't have an atmosphere, so I took it times 101,000 in order to get it in pascals. So then I put in my pressure initially to be that number that I just converted, plus 1/2 the density of fresh water times the speed, which was 1.3 squared. And then I left off those terms, and on the other side I'm trying to find the pressure, and I did 1/2 times 1,000, and this is that number that I got in the previous slide. It's just the number all the way out, not rounded. And so I had to do that first part so I could find the velocity here for the continuity or for the Bernoulli's equation. So I went through and I found the pressure, and I got 119,337 pascals. And just so it looks like a better number, I rounded it to 2 significant figures and I left it in kilopascals. So I just moved it over 3 in order to be in kilopascals. Okay, so when we talk about Bernoulli's equation, there is a number of different applications that we could talk about. So here I have a piece of paper, and if I blow across the top, that means the velocity across the top increases. And if the velocity increases, that means that the pressure is going to change. So because I have a higher speed, I'm going to have a lower pressure, and that means that sheet is going to rise. Okay, have the same thing here. It says that the low pressure at high speeds is what rips roofs off houses in hurricanes and in tornadoes, and it causes the roof of a convertible to expand upward. And it even helps with air circulation. So if we think about a house, we'll say this is my house. That means the air is going to be going up and over the top. And if it's going up and over the top, it's going to have to travel faster. And if it travels faster, that means I have a higher velocity. And if I have a higher velocity, that means I have low pressure here. And since I'm going to have high pressure down here, the high is going to want to give to the low, and that's going to create that lift. It's the same kind of concept when we talk about airplanes. On an airplane, it has a curved wing. So the air has to travel up and over the wing, which means higher velocity up and over the top, so lower pressure, and then we have higher pressure down below, and that's going to create the lift on the wing. Okay, we can also use Bernoulli's equation when we talk about tanks. So here, if I happen to get a leak over on this side, that means that I'm going to have more pressure down here because of the depth, and this velocity will come out the side. And this is going to be a higher velocity because there isn't any velocity at the top. Okay, and here they're saying if this is directed upward, that means that it's going to go no higher than the fluid level that was in the tank. So the next example, we're going to do one where we have a tank. So here we have a tank and it springs a leak. And we have to find the speed of the water that's coming out of that hole if the length is 2.9 below the surface of the water. Okay, so To start out with, the atmospheric pressure is going to be the same, so I don't have to worry about that. And at the beginning, at the very top, I don't have any velocity. In fact, I'll go back here 2 slides. You can see I don't have any velocity. And here, my pressure 1 is at atmospheric pressure, and so is it at 2. So it means those pressures are the same. So I crossed out those pressures. Here I have a velocity of 0, so I don't need that term. And here, at the end, I am 2.9 below where I started. So I'm going to say up here I have a height of 2.9. Here I'm going to say that my height is 0. So I plugged in my density, which is the rho, 1,000, times 9.81 times 2.9, because that's the height that I have. Now on the other side, I'm going to do 1/2 times the density of fresh water. I got that at the table that was on that very first slide in the first lecture, times 1,000 times v squared. And since I have 1,000 on both terms, that density, I'll get rid of that. And this would be the square root of, this 2 would move over to the other side, 2 times g times h, and square root of that to find just v. So I plugged in my numbers and I solved for v, and I got 7.5 meters per second. So that's how you can use Bernoulli's equations in a couple of problems. And that should be the end of the second lecture.